Yeah.
Okay, cool. Thank you. All right, so let's go ahead and can you guys see the notes?
Yeah.
Yeah, okay, cool. All right. So let's take a look at example number 8. All right. So with example number 8, we have a question that says determine the volume of the solid obtained from rotating the region bounded by these two curves from 1 to 3 about the y-axis. So again, that word rotating jumps out at me because then I know that I'm going to be using pi r squared for my area, okay? And I know that I have y equals 1 over x as a curve, and then the other curve I have is the y-axis. And I'm revolving it about the y-axis, okay? So let's unpack this a little bit, because as you can see, training wheels are off a little bit, right? There's no fancy diagram, so we're kind of left on our own to come up with a picture that is somehow helpful to us to figuring out what to put in our equation. So let's go ahead and sketch a diagram. Okay. So y equals 1 over x is one of those good functions to know. And that function looks like this. So it has one branch over here, okay? And then it actually has another branch over here. So y equals 1 over x comes in 2 parts. And I'm going to draw in the y-axis. Okay. And then it tells me from 1 to 3. So let's think context clues. Are 1 to 3 x values or y values, and how do we know?
Y values?
These are y values. Good. Yeah, because we're talking about things about the y-axis. So that's a good clue for us that we're going from 1 to 3 on the y-axis. So I'm going to put in y equals 1 here, and then y equals 3. Go back right there. Okay, so this is 3, and this is our 1. So when I look at what I've sketched, I'm glad I drew both parts, but I'm actually going to erase that bottom green part because it's not useful for this particular question. Because the 1 to 3 does not affect this bottom one, this bottom branch, so I can get rid of that. Okay, what's important about drawing these diagrams is you draw as much or as little as is helpful for that particular problem. And sometimes in the beginning, that means drawing more than you need to, and then just sort of figuring out what part you actually need, okay? So we're gonna rotate this region about the y-axis. And so what that means is I wanna draw my reflection across on the y-axis. So I might have something kind of like this as my reflection, okay? Now, if I kind of draw what the radius looks like on the other side, I have sort of that green line and the pink line, and sort of like this green line and that pink line, okay? And it makes sense for us to draw our blue lines going up the y-axis or perpendicular to the y-axis, okay? So when I see this, I'm going to go ahead and kind of sketch like what it might look like, all right? To me, this reminds me of like that elementary school science fair project where you like make a volcano, all right? So you have sort of like the radius at the top is kind of smaller, and then the radius at the bottom is bigger, and then it kind of looks like this. Okay, so this is my attempt at trying to go from like a 2D to a 3D. And you don't have to draw the 3D part. That part is not necessary, but I think it helps us sort of start to visualize things initially, okay? Now that axis of revolution would go like right down the middle of this volcano, all right? It would be sort of like the center of the volcano. Now, it's not a volcano in the sense that it's empty, like it's completely filled in on the inside, okay? But I'm just trying to describe like the outside shape. All right, so let's go ahead and write our volume equation. Volume is the integral of area dy, okay? And some folks, as soon as they see that word rotating, they set it up like this: pi r squared dy. So that's a really common setup that you'll see where people don't even put the pi on the inside anymore. They bump it right out to the front because they know it's a constant. So let's go back and think about what these radii might be, like what our equation could be for it, okay? So let's start with the bottom slice. So like this one right here, all right? The y value at this point is 1. What is the x value that goes with it?
One.
Yeah, that x value is 1. Okay. Well, this line right here, hey folks, I think someone might not be muted right now, so if you're not muted, maybe you can mute yourself.
Now I'm in California, so we'll see. I know for a fact that one. You have to take your wages minus $5 first, and then you would minus the 75% of the
Hey folks, if you are not muted, if you could please mute yourself.
All right. I am a big worker. It's my job.
Awesome, thank you. All right, so we've got this line right here. Okay, so that line represents the radius of the bottom circle. And that, we said, is a horizontal one, so that should be an x value, and it should be 1, okay? But if we look at this radius up here for the top circle, okay, the y value of that point is 3. What's the x value that goes with it? It's not 3. The x value is not 3.
Over 3.
1/3, yeah, because we got to put it into this equation. So 1/3, okay? And that makes sense because it's closer than the one that was at the bottom, right? The one at the bottom was 1 unit away, and the one at the top is smaller, so it should be less than 1 unit away. Now this pink line that I drew is the radius up there, and that line is represented by the x value. So I can say that the radius equals the x value of this function y equals 1 over x. Now we're going to do the same thing we did in the last problem, where we're going to go ahead and solve this equation for, we're going to solve this equation for x, all right? So if I solve that equation for x, then I'll get 1 over y. So 1 over y is going to be what I plug in for the radius. All right, so that means that 1 over y is going to go right in for the r, and I don't want to forget to square it. So I'm going to take the integral from 1 to 3 of pi is in the front, 1 over y squared dy. And I'm going to simplify that to pi, the integral of 1 to 3, 1 over y squared dy. And I'm going to rewrite this as pi, the integral from 1 to 3 of y to the negative 2 dy. Okay. So we want to make sure that we remember our power rules as well as the exceptions to the power rules. Okay. What should I change the exponent of y to if it's the exception to the power rule?
So ln.
Yeah, what exponent would tell me that my integral is going to be ln?
Would it be x to the negative 1?
Yeah, so if I had x to the negative 1 or y to the negative 1, all right, that's when I use that natural log. But if it's to the negative 2 or the negative anything else, I have to use the power rule, okay? So let's go ahead and find our antiderivative. So pi, I get 1 over negative 2 plus 1 y to the negative 2 plus 1. And I'm going to plug in 3, and I'm going to plug in 1. And this will give me pi negative y to the negative 1. Plug in 3, plug in 1. And we're going to get negative 1 over y. Plug in 3, plug in 1. Okay. Now these steps are really important to show me, especially if like a question is non-calculator. If you go straight from here to an answer, I kind of feel like you used a calculator, okay? So show me that you know how to get from step to step, and sometimes that means showing more work than you really need to, but it's also a really good way to sort of like make sure that your work makes sense to you, not just now, but maybe like next semester when you take Calc 2, or in 3 semesters when you take a different math class, that this still makes sense when you come back to it, okay? So think about it like you're really leaving yourself a trail of breadcrumbs, so show more steps than you think you might need to. But right now, I'm going to go ahead and plug in my 3, so I get negative 1/3, and then I'm going to subtract when I plug in negative 1. All right, so I get pi negative 1/3 plus 1, which equals pi times 2/3, or 2 pi over 3. Okay. All right. Any questions about example number 8? All right. Well, let's go ahead and move on to question number 9 then. Okay. So I'm going to give you a few moments to set up your graph, to try and sketch a simplified diagram like that reflection part, so you can kind of see what this looks like. And if you have time, maybe even set up an integral that would help you find the volume of this shape, okay? So I'll give you about 2 to 3 minutes to kind of try this out, and then I'll put my work up on the screen and let's see how they compare. All right, so let me talk you through my thought process as I kind of set this up. So again, I'm looking for some keywords. I see that this is being rotated about an axis, so I know I'm going to have circles. And I look at this curve over here. Y equals x squared minus 4x. And I'm able to determine that that is a parabola. And more specifically, I'm going to factor this so that I can find out where this graph crosses the x-axis so that I can sketch an accurate picture of it. So I know that this crosses the x-axis at x equals 0 and x equals 4. And so I'm going to draw a parabola on my graph. Okay. So and this parabola is facing up, so I know it kind of goes like curses. I know that it kind of goes like this and then like this. Okay. And again, if I don't really know how much of the graph I need, it's probably better to draw too much and then erase what you don't need than to draw too little and not be able to see what you want. So I know that this is the graph of y equals x squared minus 4x. And then the region is also bounded by, it is also bounded by y equals 0. And y equals 0 is another name for the x-axis. So I'm going to draw in that other curve right here. Okay. Now, what that means is the area that I'm interested in rotating is this part below the x-axis. So if I want to think about how I would approach this using area, I would think it makes sense to draw in some sample lines, and those are going to be along the x-axis, so I can tell that I'm going to be using area dx. Okay. Now, as I think about rotating it, again, I don't want to draw a whole big fancy picture, but I can tell a lot by reflecting what it's going to look like. So if I were to reflect around the x-axis, I would get sort of like this top part right here. And so this red curve represents the reflection of the green curve, or what it would look like if I was rotating it around the x-axis. And so what I get is kind of like a ball that is kind of squashed a little bit, and the ends are maybe a little bit pointy. Okay. Are there any questions so far? Okay. So if I then think about my reflected radii, like that light blue one is the reflection of the dark blue one below, and like this light blue one is the reflection of that one, and this light blue one is the reflection of that one. Okay, but I can tell that when I'm drawing these reflections, they meet at the orange line. And so therefore I know that this is a solid shape and that there are no holes in the middle. And so what that means for me in my equation is I can think about this as the integral of pi radius squared dx. Okay, so I don't need a big r squared minus little r squared. I just need the little r squared. And at this point, I can even put in my bounds. I can say that it's going to be 0 to 4. Okay. Now, they didn't tell me where to start and stop, but that point has an x value of 0, and this point has an x value of 4. So that's how I know I'm going to start at 0 and stop at 4. Okay, now let's figure out which one of these lines represents the radius. Okay, so I'm going to draw just my original region. So that was the top part was the y equals 0, and then the bottom part was the parabola. And each one of those blue lines represents a radius. So what is the radius? Or let's draw this, okay? This point has an x value of 2. What is the y value that goes with that point?
-4.
-4, very nice. And I'm presuming you got that by plugging it into this equation. And so when we look at this, that means that this line, which is my radius, that line has a length of -4. So that is my radius. Now I know this is a little bit of a weird thing to think about because a radius is not negative, okay? But we need to stay true to the picture that when we look at that y value, it's a -4, okay? What is the radius here?
Zero.
It is 0. Awesome. Yeah. And that also happens to be the y value there. All right, let's try this one. And I'll tell you that that has an x value of 3. What's the y value there?
-3.
All right, so 3 squared is 9. 9 minus 12 is -3. Very good. Okay. So it seems to me like all of the radii are determined by the y value of the function. Okay. So we can say that r equals the y value of the function. And that means that we can just use this function, x squared minus 4x. So r equals x squared minus 4x. All right, because it's already solved for y for us. And so we don't have to do the extra work. And so what I'm going to do now is everywhere I see r in my equation, I'm going to replace it with x squared minus 4x. So pi, the integral from 0 to 4 of x squared minus 4x squared dx. All right, I'll give you folks a few minutes to FOIL this out and then plug in your bounds, and then let's see what we get. All right. So finally, towards the end of class, I'm able to make it through a problem without making mistakes. But we should be getting an answer of 512 pi over 15. Okay. Are there any questions about where things came from or where things went? All right. Okay. So we've seen a few problems where we have a solid shape, that there's no hole in the middle, okay? And if we think back to sort of our starting situation, what we've done is spend a lot of time looking at this case, okay? So because it's solid, this is what folks usually refer to as disk method, because every slice is like a disk. And what we're going to move on to now, and we'll finish this on Tuesday of next week, is now we're going to take a look at this one, the case where there's a hole in the middle. And because there's a hole in the middle, this case is often called the washer method, okay? So we've seen disk method, and now we're going to take a look at washer method. All right. So this disk method can be extended to cover solids of revolutions with holes by replacing the representative disk with a representative washer. The washer is formed by revolving a rectangle about an axis. And so right here, we can see our axis of revolution, and there's a space between my disk or my washer and that axis of revolution. And so when I rotate it, that's why I end up with this hole in the middle here, okay? So we use little r to represent the smaller radius or the inner radius, and we use big R to help us determine the outer radius or the bigger radius. And then this is what we saw at the beginning, all right, where all we're going to do is take pi times big R squared minus little r squared. Now I want to clarify a couple things about the inner and outer radius before we move on to some practice problems, okay? So little r is what we call the inner radius, okay? But it is also it is determined by the curve, oh my gosh, curve closest to the axis of revolution, okay? So like this curve right here is closer to the axis of revolution, and so that makes this hole in the middle. In contrast, big R equals the outer radius, but it is also defined by the curve farther away from the axis of revolution. Okay, so the green curve would be the one that makes sort of the outer shape, or it would be the one that has a bigger distance from the axis of revolution. Okay. So it's probably even more important that we can see this on a diagram for washer method, because we have to make sure we have the right inner radius and the right outer radius, okay? So let's take a look at an example, all right? We're gonna try example 10. And so now we're back with those fancy diagrams that I found on the internet, and I hope those are helpful in getting us to visualize what's happening, okay? But I will also show you how I would draw the diagram if I didn't have all the fancy technology. So example 10 says, determine the volume of the solid obtained by rotating the portion of the graph of the region bounded by y equals the cube root of x and y equals x over 4 that lies in the first quadrant about the y-axis. So we've got two functions here. We've got this y equals the cube root of x, which corresponds to the red line in the graph below. And we have this line y equals x over 4, and that is representative of the blue line in the diagram, that first diagram, okay? Now, what we're gonna do is we're gonna rotate this, all right? So I'm rotating, so I know I'm gonna use either pi r squared or pi big R squared minus little r squared. And I'm rotating it about the y-axis. And that's why there's this little arrow right here to show me where I'm rotating it. And this is my axis of revolution. Okay. So when I revolve it, and I use a fancy computer-generated diagram, I can see that it kind of looks like a cone, but part of the inside has been scooped out. All right, so take a look at that for a moment. Make sure that you can see that part of the inside is missing. Now, when we move on to this second diagram, okay, so more of a stripped away version, what's nice about this one is you can see the washer. And what I mean by that is we can see that there is this outer ring, okay? And that outer ring is blue because it's made by this blue line, or our y equals x over 4, okay? The inner radius is this one, and that inner radius is red because it corresponds to this part of the graph, and it matches this y equals the cube root of x. All right, so take a moment and just look and try and convince your brain to let you know that you see this washer right here. All right, I'm going to add one more thing into this diagram that they didn't put in here, but I think might be helpful for us. So if I take the inner radius and I subtract it from the outer radius, I will get this line right here. That purple line is this purple line. Okay, again, this purple line, the difference between the outer radius and the inner radius is this purple line. how long is that purple line at that point right there?
Would it be 4y minus y to the third?
Yeah, but what is that at that point? Like, give me a number.
I don't know in that case.
All right. So I love that you're able to tell you have to subtract the 2, okay? Now, if this is right at 2, let's plug in 2 for both of these cases. So 4 times 2 is 8 minus 2 cubed, which is 8. So we would get a purple line that is 0 units long. And that kind of makes sense because, let me go back and right here at the very edge, the curves are exactly the same. So that washer has an inner radius and an outer radius that are exactly the same, okay? That happens one more time in their graph. It happens right down here at the bottom, that the inner radius and the outer radius are exactly the same. So I'm going to get 0 for that purple line. But for all the other purple lines in here, I can find the length of that line by doing exactly what you said, which is 4y minus y cubed, okay? That will give me the distance between my outer circle and my inner circle. Now, I know that the diagram says 4y and the diagram says y cubed, but how did they get that?
Solving for x.
Yeah, they solved for x, right? So we have these equations, y equals the cube root of x and y equals x to the 4. Now, one of the things that probably they were thinking, okay, before they put together all these diagrams is, when I think about the purple lines, I'm stacking them up the y-axis. And these lines are perpendicular to my axis of revolution. And so that tells me that I want to do dy and not dx. And we know that if we're doing dy, we need our equations to have y's in it and not to have x's in it, okay? So that's why this is a 4y and a y cubed, and it also represents that horizontal distance, okay? So we need an x equals. So let's use all that information to set up our volume formula. So we get that the volume equals the integral of area dy, okay? And because I know I'm rotating it, I've got that pi r squared formula for my area. So I'm going to put the pi out in the front. I know that my bounds should be y values, so I'm starting at 0 and I'm ending at 2, okay? Now, if I didn't have this graph, how else could I find that my bounds are from 0 to 2?
Set them equal to each other.
Yeah, you could go ahead and set them equal to each other, okay? And when you do that, you'll still get 2 and 0, but you want to make sure that you're finding y values, okay? So now I know from my diagram that I'm going to need washer method because there's a hole scooped out of my cone. So I'm going to write big R squared minus little r squared dy. Okay? And now I'm going to use these equations where they already solved it for y for me. Okay, so pi, the integral from 0 to 2 of the big R squared is 4y squared, okay, minus the little r is y cubed, and I'm going to square that. Okay, so together, that will help me find out what happens when I have a circle missing from the inside of a bigger circle. All right, let me give you a few moments to distribute here, start to find your antiderivative, maybe even plug in your bounds, all right? All right, so we should be getting 512 pi over 21. All right, how we doing out there in cyberspace? Any questions about example 10? All right. So folks, here is your exit ticket for today, okay? So listen to these directions carefully. I'm gonna have you take a look at question 11, all right? So question 11 is similar to number 10, but some things are a little different, all right? And what I'd like for you to do is to set up, but do not solve. Okay, so all I want is the setup and the diagram. Okay, so just to show you what I mean from example 10, all right, I'm looking for some sort of addition to the diagram, so more than just the picture that you're given. And I'm looking for up to this step right here. Okay, so the setup. I want to know how see, do we know what our outer radius is? Do we know what our inner radius is? And how do we plug those into the formula? Okay, because if these two steps in the green are not feeling solid, then the rest of your problem it doesn't really matter. Okay, so I want to make sure that we feel very confident in this setup. So we're going to try it today. Based off of that, we can sort of direct Tuesday's lesson, because I can see like who's really feeling solid, how many of us do, and then how many of us are maybe feeling like we're not quite so sure. Okay, so go ahead and you're going to draw a diagram. You're going to add a little bit onto it. And then you're going to do the setup for the integral, and you do not need to solve it, okay? And so I'm just going to move this back up here so you can see question number 11. And I'm going to ask that you send that to me by 12:30, okay? So again, add more to the diagram, write the integral that you have for your setup, but you don't need to solve anything, okay? You don't need to solve it. And that's where we're going to stop for today, okay? So I'll give you a moment to either copy that problem down or take a quick picture of the screen so that you can do that. And I'll stick around for the next few minutes in case anybody has any questions. But if not, you're welcome to take off.